Chapter 27, Part B, and this is on models of atom. Bohr model and spectra. Okay, so you look at the atom. All right, atom is composed of, you look at the simplest one, hydrogen with an electron orbiting around somehow or somewhere this thing. All right, the other early models of the atom for higher ones was what they call the plum pudding model, which was this kind of large mass of positive charge intermixed with negative charges like little raisins, and this was called the plum pudding model. Okay. And that's what stood around for a long time as far as that was concerned. At the same time, in 1883, Bohr discovered the spectrum that light, that looking at a gas spectra from, say, hydrogen, this is similar to what we'll see in the lab, is you would see instead of a continuous spectrum like you would see from an incandescent lamp, you saw individual lines instead. And this was kind of confusing, all right? So why did you have these individual lines? Instead of a spectrum. And then in 1911, Rutherford was doing experiments on shooting alpha particles, which is a helium nucleus of 2 protons and 2 neutrons, and he was shooting them at very, very thin sheets of gold, extremely thin. They were transparent. They were so thin, and he would shoot these at these, and for the most part, they would go through. And he was trying to understand what was made up of this material, but occasionally one would bounce straight back. So he'd shoot them at this gold film, very gold thin, and some of them would come straight back. And he said this is the same analogy as if I shot a cannonball at a piece of toilet paper and it came back. So this made no sense until they reanalyzed it, their model, and realized instead of the atom being this whole thing, where again, this is about the size, this is about 10 to the minus 10 meters, size of an atom. Instead, what you have is the atom is mostly composed of an extremely small nucleus, which is about 10 to the minus 15th meters, which is 1 femtometer, and surrounded by this electron shell, which was on the still 10 to the minus 10th meters. Now, both of these are small, but this is 100,000 times. This is 100,000 times greater than the diameter of the nucleus. So even though the nucleus made of protons, it's extremely small dense. So this is what the atom actually was. And what they realized then is this is how it is, and the electrons are somewhat orbiting this. So that's what the modern model of the atom became, is this extremely small, dense nucleus, extremely dense. So the atom is actually by far mostly empty space as far as that's concerned. and then tried to reconcile this with the spectra, and I'll leave that out for a minute. Those are what Rutherford discovered. So this is what we have for the model. So the plum pudding model went out the window. All right. So that was gone. And in 1913, Niels Bohr developed a model of that for, say, hydrogen, and this is related to the lab 12, I believe, or 13. Anyway, it's related to the lab, no, 12. And what you have is you have these orbits, sort of. You know, don't take them like literally. And they're given by n equals 1, 2, 3, 4, and so on. And what you're actually seeing is the electron would be orbiting somehow. I mean, it's not really orbiting like a planet, but it'd be in this higher energy level. And when it dropped down to, in the case of the Balmer lines, say 3 to 2, it would emit a photon of light. Right? And if it came from 4 to 2, it would emit another photon of light, different photon. If it came from 5 to 2, it would be more. And this is what was made up of the hydrogen spectrum. And that's what the model was. So that was for going from higher numbers, so like n equals 3 down to n equals 2. That's in the visible spectrum. If you go from n equals 3 to n equals 1, that is in the UV spectrum. And that's the so-called Lineman Series. And if you're, say, going from n equals 4 down to n equals 3, that's in the infrared, and that's called the Paschen series. So this was discovered first, so it's going down to n equals 2, and n equals 1 is what they call the ground state. All right, that's the lowest energy that can become, and what we're actually seeing is instead of the electron orbiting wherever it wants to be, and again, these are not, don't take these literally, but it works, is when it drops down, it emits a photon, or if it's here and the photon hits it, it'll jump up to higher energy. So this is all part of what we call quantized states. And this explained, and this model explained the hydrogen atom extremely well. So let me summarize this then, down below. So we'll get rid of this. And so what we have here then, and this is the model, so this is the formula is 1 over lambda is R times 1 over 2 squared minus 1 over n squared. And that is for, where this is what they so-called a Rydberg constant. And that is 1 meters to the minus 1. Right? Okay, that's so-called Rydberg constant. So this will give you the wavelength of for hydrogen totally, only for hydrogen. And the only reason it works because hydrogen composed of 1 electron and 1 proton. So this was a relatively simple formula to explain all of that as far as that. Now, this formula only works for hydrogen or hydrogen-like atom. It does not work for helium, even helium. Because you have helium, you have two electrons. The complication of the electrons or interacting with each other makes it a far more complicated process. So, as we have here, so for the Lineman series, so for the Bohr series, you have 1 over 2 squared minus 1 over n squared, where n is 3, 4, 5, and so on. For the Lineman series, this is actually 1 over 1 squared, and then n is 2, 3, 4, 5, and so on. And then for the Paschen series, this is 3, and then you end up with n is 4. So I'll say Bohr, Lineman, Paschen, 4, 5, 6, so on. All right? So if you have 2, then you have the Bohr series, which gives a visible spectrum. And that's the basis of one of the labs 11 and 12 are dealing with this characteristic. So that's what we have here, and it does get kind of complicated a little bit. And what we have then, so can show this a little bit clearer. This diagram in the book is very good from that. So the left one is the Lineman series, going all the way down to n equals 1. The Bohr series goes down to n equals 2, and the Paschen series goes down to n equals 3. All right. And let's see. Oh, almost done here. All right. So related to this then is then the energy of each level. So we leave this. So if I clear this up a little bit, I'll leave and you'll see this when you do lab 12 is all right. The energy of the ground state, and I'm not going to get into details, but the energy of this ground state, E1, is given by, or any level, is minus 13.6 electron volts. We talked about what electron volt is, over n squared. What this means is that this is what we call a bound atom. All right, because this is negative, its easiest state is to be negative. So for n equals 1, then E sub 1 is minus 13.6 electron volts. Meaning this is the energy of minus that. So to be able to knock that electron all the way out, if I hit that with a photon of given by energy of h times the frequency, or h is Planck's constant, f is a frequency, we're not going to get into that, of 13.6 electron volts, and you can figure this out in joules, then it will knock that electron all out, and that will actually ionize it. And again, this is only for hydrogen. It will ionize it. Get that. And if E2 is minus 13.6 over 4, which would be minus 3.4 volts electron volts. E3 is minus 13.6 over 9, which is 3 squared, is 1.51 electron volts, and so on. So what it means is, if I go from 0, 1, all the way out to ionized, I get 13.6. If I go from 1 to 2, right, this one, E1, has an energy of minus 13.6 eV. E2 has an energy of minus 3.4 EV. The difference going from 1 to 2, 1 to 2, is a difference of 10.2 electron volts. So if I'm in the ground state and I hit it with a photon of 10.2 electron volts, it will go up to the second volt. So it actually would be 3/4 of the way out of the atom. Just going up here is 3/4 of the way. So in reality, if we actually were to kind of sketch this more realistically, as far as energy levels, then what you would actually have is, this is the nucleus. Here's our first state. Our second one would be way out here. Our third one would be about here. And they get progressively closer until they get infinitely close. They get closer and closer and closer and closer. So this will be 1, 2, 3, 4, 5, and they get infinitely. So this is a change of, this is minus 13.6, this is minus 3.4, this is minus 1.5, and eventually this becomes 0 pretty close. So you can see they get closer and closer and closer. So the farther it is away, the easier it is to actually ionize this point. So if I was to go from here to here, it would only take 3.4 electron volts to actually ionize it the rest of the way. So that is the Bohr atom, and that is the rest of chapter 27.